techniques, and we have some MCQs based on those. Some compaction techniques that are based on fabrication of the materials from 2D shapes, 3D shapes, and various types of process parameters that are involved in such processes. So we'll do first some MCQ type questions and then a few numericals. So it will be a comparatively a shorter tutorial today. So first we'll try to cover some MCQ based question. So the first question says, to get a 3D compact, which powder shaping technique will be employed? So we are being asked that we want to get a 3D compact. So which of the techniques should we use?
Madam, slides are not changing. Slide is
Okay. Is it still not changing?
no, ma'am. It's seen as first slide only.
Okay,
Title, powder metal.
okay. Is it changing now?
It's been presented to the first slide. Only second, whatever. The question is that is not.
I,
Now it is changed 600 to 100.
yeah, okay. So now we can zoom. So I think first we have a question that says to get. So is it clear, right? So should we start?
Yeah.
Okay. So the question says that to get a 3D compact, which powder shipping techniques will be employed? So we have different types of powder shaping techniques. Some is deep casting, extrusion, slurry casting, injection molding. So you have to say which of these techniques is used for 3D compacts. So you can answer the question. Can you answer the first question?
I think injection molding.
Okay, so
Injection.
one of the options is injection molding, right? Because by injection molding, you can create a 3D compact by first injecting the mixture of our powder and binder into the mold and then getting a desired shape based on the type of the mold. This 3D casting is actually a 2D technique. This tape casting is actually a 2D technique. So you will have some flat surfaces out of it. So for tape casting, you will have a 2D shapes available. For extrusion also, you will have some long, like a flat but long type of bars for extraction. For compaction, so you will have also 2D shapes. Also, the right answer is slurry casting also, because in slurry casting also you are trying to get a mold based on your mixture of binder and powder, and that binder and powder is then made to flow into the mold. So slurry casting and injection molding both are right options for 3D compacting. Now next question is that the temperature needed to debind the compact completely is 600 degrees Celsius, 200, 100 or 1000 degrees Celsius. We have to tell at which because what we are trying to take, we are taking a compact for compression or for compaction in order to get a compacted mold or compacted bed of our powders, right? Because we are trying to convert the bed of powders into a material. So we are trying to compact the material, and during compaction we might have added certain binders to it for particle like interactions, for filling in the voids between the particles and particles. But this binder needs to be removed before we go for the further processing such as sintering, because this binder will create porosity in the subsequent step. So this binder is removed prior to going for uh, the sintering. So for debinding, what we can do, we can either go for a temperature treatment where we will heat the powder mixture, and up to a certain mixture where these binders can be removed from the compact, or we can do some solvent treatment. So what happens actually in both the techniques, we are trying to, because most of the times the binders are the organic material, so we are trying to attack the organic materials either by heating them. As you know, if you heat a material, if it is an organic chain, polymeric chain, it will try to degrade into smaller polymeric chains, and the polymeric changes will be released in the form of gases, say CO2, H2O, depending what kind of a polymer you are using. And also solvent will try to dissolve, because based on the principle of chemistry, which says that like will dissolve like. So you can use some organic solvent to dissolve your binder from the powder mixture. So both of these techniques can be used. Here we are talking about the temperature. So at what temperature do you think that this binder needs to be removed? So which is the right temperature? What is the answer?
600 now?
Right, the answer is 600, because at 600 degrees Celsius, the binders mostly are removed from the powder mixture, and then we can subsequently put the powder mixture to sintering processes. So then we have another question that says the parameters needed for successful molding are high pressure, low viscosity, high viscosity. So basically, when we are trying to mold any powder mixture, what we are trying to do, we are trying to put it in a mold, and then we are trying to compress it. So there are basically two process parameters that are significantly affecting the quality of your mold. So this is one is the pressure, at what pressure you are trying to apply the material, and then another is the viscosity. This is the viscosity of your say powder which is being filling the mold. So the viscosity of your mold powder mixture or powder slurry or powder binder mixture. So if the viscosity, firstly if you talk about viscosity, if viscosity is very high, so if there is a fluid which has a higher viscosity, so its flowability will be low, so it will not flow very easily. So its flowability low, so it will not be easily and homogeneously distributed in the mold. So high viscosity is not desirable for a good mold. What we are requiring very low viscosity, so that we have a good flowability, and the powder flows throughout the mold. So one option out of this is based on viscosity. So you can say low viscosity is the one parameter. Now what can you say about the pressure, the high pressure and low pressure, about the parameters that you are needed for successful molding? There's also one option related to the pressure, so you have to say which of the two is correct. Out of the viscosity, we know that low viscosity is the correct option. For pressure, what is the correct option?
Pressure should be higher.
Okay, so if we say that we have a high pressure, why is it is required high pressure? Because if you have seen one of the graphs like this, it would be something related to pressure and it would be related to your green strength. So as you increase the pressure, the green strength also increases and it then saturates at some point. So we say that as you are increasing the pressure, you are actually trying to make certain changes in the structure. Well, the structure is by rearrangement of your molecules, by like the particle particle interactions between your binder and mixture, or between your powder particles. So there are different stages of compaction that happen. There are rearrangement, there is elastic deformation, there is plastic deformation. At plastic deformation, all the voids are tried to be like covered by the compaction, so you are trying to minimize all the voids between in the particles. So for that, high pressure will be required. So the right option is high pressure and low viscosity. These two are the right options. So then we can move to next question that says, as the mold is filled in an injection molding process, the viscosity increases, decreases, increases, and then decreases, remains constant.
think it decreases now.
Okay, yes, because we want to have a higher uh, this filling of the cavity, but when you're trying to normally fill the injection molding, the viscosity is very high. That is why there are some heating coils attached to to increase the viscosity for the injection molding presses. So normally the viscosity is high, but the desirability is that we should have a low viscosity. For that, we are trying to add some heating coils at the injection chamber below before the injection chamber to decrease the viscosity of the melt or the slurry, we can say. So the desirable is low viscosity, but actually the viscosity is very high when you are trying to put it inside the mold because of constrictions in the setup. So the right answer is that the viscosity actually increases, but when you are trying to put it inside the material, then you are heating it with the system. You are have a heating system that decreases the viscosity. So the right answer is A. And then we have another question that says during injection molding, pressurized cooling is used in this stage. In which of the following stages the pressurized cooling is used? So you have to say there are different stages, like you are filling the mold, you are closing the mold, you are ejecting the mold. So based on what kind of stage you will expect a pressurized cooling to happen out of these parameters.
Re-
See, mold
Recovery.
actually what happens when you're trying to go for actually the pressurized cooling happens during for example in your mold ejecting or mold recovery is actually just a phenomenon where you're trying to recover, yeah, like take out the mold from the injection mold, because it is a phenomenon, it is not a process that you're taking place. It happens because there are some release of the stresses, so recovery is not the right option because you're trying to use pressurized cooling in processes where you have, say for example, mold ejection. So in mold ejection you can have a release of you can have a pressurized cooling, and then will help you to release the stresses and eject the mold. So option C would be right. Then in another question we have, in an injection molding system the homogenization of the slurry happens in mold, injection system, loading hopper, or ejector. So we know that basically when you are having an injection molding chamber, you have two setups. One is the injection system molding setup, setup, and another is the mold. So this is where actual formation of the compact takes place. This is from where you are feeding it into the mold. So there are basically two systems, broadly two systems in an injection molding system. So you just have to tell that the homogenization of the slurry, where it happens. Is it in the mold? Is it in the injection system? Is it in the loading hopper, or is it in the ejector? See, in the ejector, the homogenization is not required, because by that the powder will be compacted and there will be a significant heterogeneity in the material. So at the ejector, the homogeneity of the slurry will not be required. It will be of no use. So it should be somewhere in out of these where you want to have a homogeneous slurry. So you can answer that. What could be it? It could be mold, injection system, or loading hopper.
In injecting system.
Right. In injection system, it is better to have a this homogenized slurry, because what you are trying to take, you are trying to mix the binder and the powder. So in the injection system, if you have a homogenized slurry already, then you can inject it in the mold and you can expect a uniform distribution of your particles for the compaction. So the right answer is injection system. Then we have another question that says that the typical amount of binder that is usually added in a PIM process is 70, 35, or 40. So what is the volume percentage of binder that is required in injection molding?
probably 48.
Right, the answer is 40% of the binder is added, because this needs to be optimized. If you have a very low binder, then you will not have a perfect particle-particle interactions, and then that will be compromise your green strength. But if you have a very high binder, then that is also a problem, because then there will be a large amount of like binder viscosity in the material. Because of the binder there will be large viscosity, and that will prevent your homogenization. So it needs to be optimized, and 40% is roughly the right amount for of binder that will be required. And then we have next question that says that at critical solid loading, the mixture density is low, the mixture density is at its peak, the mixture viscosity is minimum, mixture viscosity is maximum. So actually what we are trying to say that when you have a mixture of the powders, if we know that the mixture of the powder and the binder, so that will be dependent on your say we know something, it is dependent on your powder content, and it is dependent on your solid loading capacity. It is somehow related to this, right? So it is somehow related to like this. So we can say that it is related to, this is your powder content, how much powder you are adding, because that will affect your viscosity. And this is the critical loading, solid loading. So this critical solid loading, you need to tell what it is related to. It is the mixture density is low, is it related to that? Is it mixture density is at its peak, or mixture viscosity is minimum, or mixture viscosity is maximum? At what conditions are you defining a solid critical solid loading? So the right answer is that when you have a mixture density is at its peak. So this is defined for a highest mixture density, and when we have a mixture viscosity is maximum, and it is said that it will tend to infinity. So this is a critical loading for a solids for in a mixture, that will be defined by as how much the viscosity at this point and this critical loading, the viscosity of your mixture will be highest and the density will be at its peak. So this is something that is defined by the critical solid loading. So this is the maximum loading of your solids that you can do in a mixture with the highest viscosity, highest density. So this is how it is defined in this equation. Then we have another question that says that in PIM process, binder is removed while feeding from the hopper, while homogenization in the injection system, during pressurized cooling, or after mold injection. So where is exactly is binder removed? So if you are feeding from the hopper, obviously you will not be removing the binder at the feeding system, because you want to make a compact. So when you are feeding it through a hopper, at this stage you will not be uh, uh, removing the binder. So this is not the right option. Then we have while homogenization in the injection system. This is where you have an injection system and you are trying to feed it with the powder. So here you are asked to remove a binder. Also here the binder will not be removed, because you are trying to homogenize the powder with the help of a binder. The properties of the binder are being used in this stage. So also in this stage we will not be removing the binder. So we will be then pressurized cooling. Once we are pressurized cooling, we are trying to make it a compact. So this is also a stage of compaction. So in this stage where we are trying to have a pressurized cooling system for our mold, we will not remove the binder, because the properties of the binder are still required. But after mold ejection, we do not need the properties of the binder, because now we have compacted all our powders and we can remove the binder for further processing. So this is only after you have done all your compaction processes, whether it is feeding, injection molding, or cooling. After that only you will remove the binder. So the right option for binder removal will be after you have injecting the mold. So the option D is right. So now we have another question that says that spring back during ejection is prominent in fine particles, coarse particles, spherical particles, spongy particles. You have to say which of the following will have a higher spring back. So what happens actually during spring back? There are actually during when you're trying to compact a material, or you are trying to compact the mixture of your powder and binder. After the compaction, the grains or the particles are under stress because they have accumulated some stresses during due to the plastic deformation processes. As you are trying to eject the material, because now you have removed the compaction pressure and now you are trying to remove this mold. As you are trying to remove this mold, there are some stresses which have accumulated in the material and they are trying to get released. As they are being released, they are trying to, this is a process which is called a spring back. The spring back occurs during the ejection process because the stresses that have accumulated, they're trying to get released. Because of this high release of the tensions, release of the stresses, there is possibility that there could be cracks in the material because of the release of the stresses. So it will cause defects in the material afterwards. So the spring back should be lowest for a material. So you have to say that which of the following will have a highest spring back. Is it fine particles, coarse or spherical or spongy powders? You can
I think
answer.
fine and spongy. Fine
Uh,
and spongy.
right. Right, the fine particles will have a high spring back because there are a limited number of like there are very smaller distances by which the dislocations can move through the material. So there are chances of release of the stresses at much higher speed. Similarly, for the spongy particles, we can have a higher spring back during the ejection process. Now we have another question that says which of the following process takes place when hard powder compacted at lower pressure. So you know that there are powders, they have, we know that the powder characteristics such as morphology. So we have seen that there are powders, the properties of the powders such as your morphology of the powders that affects your compaction. Similarly, the if you know the morphology of the powder will be affecting your compaction, the strength of your powder will affect your compaction process. So also which is the hardness of the material will affect your compaction process. It will affect how your compact will behave. So you are saying that even hard powders are compacted at low pressure. What of the following process occurs? Is it plastic deformation, fragmentation, both plastic deformation and fragmentation, or it does not affect? Remember, we are talking about hard balls, hard powders. So what could be the right answer for this? Which of the following process takes place for hard powders which are compacted under lower pressure? Basically, as we uh, basically you also saw that we have some graph that says that the strength increases as you increase the compression pressure, right? So there are two chances that you have. You can have say for example soft powders and hard powders. For soft powders, basically when you are trying to compact the material, you are to compact the mixture, there are chances that first it will go through rearrangement. After rearrangement, there will be elastic deformation, and then there will be plastic deformation, and this plastic deformation helps in the compaction processes for soft powders. But because we are hard powders, the chances for hard powders is that initially at low pressure it will undergo plastic deformation. But if you are trying to increase the pressure, if you are this is at low pressure. At low pressure, what happens that for hard balls, they undergo plastic deformation. But if you have a high pressure, at very high pressures, what happens? The particles tend to fragment. So there will be fragmentation because they will not be able to sustain the high pressures because they are ductile. They are not ductile, they are brittle. So at high pressures, they will go fragmentation. But here, because we are asked at lower pressure, what happens? So the right answer will be that they will undergo plastic deformation at low pressure, but at high pressure the hard powders will undergo fragmentation. So you need to know that how your properties of the powder, which is if it is a soft powder or it is a hard powder, and how it will affect your compaction process. So for hard powders at low pressure it is plastic deformation, for hard powders at high pressure it is fragmentation, and for soft powders it is the elastic and plastic deformation. So now we have another question, which says that the green strength mainly depends on the dash of the particles, the morphology, the specific surface area, particle size or shape. So you have to answer what is the parameter that is affecting your green strength. You can answer this question. Can somebody answer this question? First, if you see morphology, is it affecting your green strength or not? Will it affect your green strength? A particle size, okay. And any other factor? Actually, what happens that we are talking, these questions are as you can see, the all of the options could be right, that the morphology of the particle affects your green strength, because you might have seen that there is the difference. If you have a spongy morphology of a particle, the compaction will be different, or if you have a completely dense material, the compaction will be different. So the morphology for your densification will affect the green strength. Also the specific surface area will affect, because what is basically the specific surface area? For a larger particle, the specific surface area is small, but if you have a for a very minor particle, the surface area is increased, right? So the surface area increasing can also affect your interparticle work hardening or interparticular frictions, and that will impact your compaction. So both of these are the direct consequence of your green strength and effects of the particle. While if you say particle size, the particle size is actually a function of your specific surface area. So you can say, because we are talking about mainly dependent factors, so you can say that morphology and specific surface are the generic terms that will affect your green strength, while particle size is a consequence also because of a surface area, and shape also because it is a morphology related. So we are talking about morphology. Basically, we are just talking about the morphology and the specific surface area for the green strength, and that will affect your densification processes. So option A and B are your direct correlations for the green strength, but in general, all of these parameters are affecting the green strength. So next question is, when hard and soft material powders are mixed, the compact ability depends on the connectivity of hard powders, the connectivity of the soft powders, the concentration of the hard powders. Can you say what happens? Because normally, soft powders and hard powders will have a different response to our compaction, right? Because as I said, that at low pressure, the hard powders can go under plastic deformation. Both can go under plastic deformation, but at high pressures, there is a chance of fragmentation for the hard powders. Also, because there are interparticular frictions, and that will result in decreasing the density of your material. So, what is the best parameter to decide for a mixture, the compactability for a mixture? First, it is the connectivity of hard powders, because when you have powders, how they are trying to connect one another with the help of a binder by making some bridges with them. So that connectivity of the hard powder is important because that will determine your compacting ability, right? So this option is right. But the connectivity of your soft powders is not a significant parameter when you're trying to talk about a mixture of hard and soft materials, because soft materials have an inherent tendency to undergo ductile transformations or undergo plastic transformations. So the connectivity of the soft powder is not much of a factor here, but the concentration of the hard powders is an important factor. If there are large number of hard powders in the material, there are chances that the material will undergo higher amounts of interparticular frictions, and that frictions will result in less densification of the material, or it will result in fragmentation. It will result in decrease of the grain strength. So the largely the hard powders are the main influencing factor when you have a mixture of hard and soft powders. So you will always check for your hard powders, the interparticular connections between the hard powders and the concentration of your hard powders when you are operating in a mixture. So option A and C are the right options. So for this question you can answer. This is the question that says that dash is the usual pressurizing medium in cold isostatic pressing. So cold isostatic pressing is nothing. We are just trying to have a equal pressing in all directions, a uniform pressing. So it is isostatic means the same pressure is being applied from all directions. So this is a cold isostatic pressing. So you have to say what is the usual pressurizing medium. So dash is the usual pressurizing medium and conducted and dash temperature. So you have to fill two blanks. First is that it is a water treated with corrosion inhibitor and at ambient temperature we are trying to cover it. Option B is that water treated with corrosion inhibitor and liquid nitrogen. Third is untreated water and liquid nitrogen, and then we have untreated water and ambient, atmospheric air and liquid nitrogen, oil and liquid nitrogen, all of the above. So what is the usual pressurizing medium? So we are talking about the usual pressurizing medium. Generally, what is the medium that is operated? So you can answer this question.
Water treated with corrosion inhibitor and ambient.
Right. So the option A is right, that you're taking the water treated with corrosion inhibition as the pressurizing medium, which is outside this mold, and then you are conducting it at room temperatures or ambient temperatures. This is the right option. Now next question says that cold isostatic pressing has dash variations of presses and identified based on the dash. So it is having that we have how many variations of cold isostatic pressing are obtained, and they are based on what they are distinguished on what basis. So basically you are saying that you have a cold isostatic pressing, it has some two types. You should know what are the two types and on what basis is this characterization done. So the first is that it has two types and the characterization is done on based on the vessel, pressure vessel. It has three types and the characterization is done on pressure vessel. It has two types and the characterization is of pressure generator 3 and pressure generator 3 and elastomer mode 2 and elastomer mode. So can you tell what is the difference?
Yes, I think two and elastomer.
Yes, 2 and elastomer. So actually we have two types. Can you name the two types that we have for cold isostatic pressing?
Dry bag and wet bag.
Right. So we have two pressings. We have dry and wet. And on what basis is this distinguishing? This is based on how we are taking the mold. It is actually based on your elastomer mold. If it is already inside the pressurized vessel and you are taking it every time out from the vessel, then it is a wet mode, right? But if it is present inside the mold and you are not removing it, it is not a removable mold, but it is present inside the pressurized vessel with some outside membranes just keeping the mold dry, then it is a dry mold. So the distinction is based on your type of mold, and there are two types of molds, one is dry and one is wet. So next question says that I think this is dash is the unique aspects and dash is the recognized limitations of cold isostatic processing. So you have to say what are the advantages and the disadvantages of cold isostatic processing. So first is that shapes with high ratios of length to height can be constructed, but it has a rough surface finish. The uniform density of compacted bodies is a unique aspect, and the production rate is low is the limitation. Then see that the short life mold is the unique aspect, and the low cost of the mold is the limitation. The D option says that the organic binder not required and leakage of the mold. That is one of the options. And then we have precise dimension control and hard to prepare composite structures. So you have to identify what is the combination of unique features and limitations. You can answer this question.
Uniform density of compacted bodies and production rate is low.
Okay, so you mean to say the option B is right. It says that you can have a uniform density of compacted bodies, obviously, because this is a cold isostatic pressing where we have equal pressures from all directions. So you will have a uniform compaction as compared to axial compaction, say for example. And the production rate is low. That is one of its drawbacks, right? And any other option that you say is right? Actually, the option A and D are also right because shapes with higher ratios of length to height can also be created because it's just the mold property. So you can fabricate the mold and you can have different types of different edge body ratios of shapes. But the surface finish is not very smooth, right? So that is the problem. And also organic binder is not required in cold isostatic processing. You are just letting it flow in a mold, so there is no use of organic binder, but there could be a leakage of the molds inside a highly pressurized vessels. So if you are especially having a hollow hollow parts or hollow fabricates hollow types of parts you are fabricating, so in that case leakage will be a problem. So these are the advantages and the disadvantages of your CIP process. Next is that which one of the following particle size aids the sintering process in powder injection molding. So for a powder injection molding, if you know, there is a limitation that you should use a certain particle size for a powder. So based on what is the particle size, which of the option is right? Which is the best option for sintering for these type of particles? One is 1 to 20, 0.1 to 20, 5 to 20, 10 to 20, 20 to 25, 20 to 50. What is the ideal particle size for required for a powder injection molding? Do you have any idea
1
what
to
is?
20. Okay.
Okay, 1 to
First one,
20.
1 to
Actually,
20.
for a powder injection molding, we do not have a lower limit, but we usually say that less than 20 micrometer is the particle size that should be utilized for power PIM. So this is less than 20, this is less than 20, this is also less than 20, this is also less than 20. So all the first four, I think first four options are right for this. So this is the particle size limitation that is required for a powder injection molding. Is it clear?
Yeah. Yeah.
So now this is a important question that says that in powder injection molding, feedstock is prepared by mixing 85 volume percent of binder with respect to powder. So they are mixing the binder of 85%. So you have to say which of the following is the correct statement. The first is that the formulation can form successful feedstock, because what will be a successful feedstock? The successful feedstock will be if you have a if you if you have a particle-particle interactions with the liquid bridges that are being formed with the help of a binder, so that will be a perfect formulation. So it says the formulation can form successful feedstock, or it is an insufficient binder quantity, so all the voids between the particles cannot be filled. Third option is that the excess of the binder quantity and separation of the powder and the binder. Four is excess of binder quantities to coat the particles with binder to break the agglomeration and to attain uniform distribution of binder and particle size. So which of the options is right? at mixing of 85 volume% of binder.
Third one, I guess. Over excess.
Right, so because one of the option is that excess of the binder is being used, because what is the required volume? It is 40%. So you are using actually greater than the binder volume for a mixture. If you have excess, the separation of the powder and the binder, because there will be no interactions between the particle and particle, and because of the excess binder, then we do not have enough particle interactions which is required with the help of a binder. So this is right option. And also, if you see that this option says that excess of binder quantity to coat the particles with binder. This is also true because you do not have a sufficient, you do not have the coatings of the particles with the binder sufficiently, because now there is too much binder around the particle. If this is your particle, then there is too much amount of binder around it, which is not allowing the interactions between this particle and this particle. So it is causing insufficient coating of the particle with binder. So you have to break the agglomerates and then you have to attain the uniform distribution. So this is also one of the right options, right? Now we have another question that says that the correct sequence of powder injection molding is, what is the correct sequence out of these? The formation of feedstock, molding, sintering, binder removal, formation of feedstock, binder removal, molding, sintering, formation of feedstock, sintering, binder removal, molding, formation of feedstock, molding, binder, sintering, mixing, molding, binder removal, sintering, formation of feedstock, heating, binder removal, and molding. These are different combinations. You just have to say what is the sequence for a powder injection molding. First, you should know that.
Formation of feedstock,
Okay.
molding, binder removal, then sintering.
So you are saying this option is right, right?
I think fourth one.
Yes, that is right. Because first you will form a feedstock. Formation of feedstock means that you will try to mix your powder particles with the binder. So that is formation of feedstock. Then you will mold it. You will send it to a mold. Open the mold. Put your powder inside it. Close the mold. And then after molding and like ejection of your mold, then you will go for binder removal. This is after your molding process, because you have to remove the binder that is present. So then after you will subject it to sintering. So this is the correct sequence for a powder injection molding technique. Now we have another question that says dash mold is used in slip casting and absorbs the binder by dash action. You know, in one of the methods that we have one of the is slip casting. This is a slurry casting technique where you are having your powder mixture and powder and binder are being mixed together, and they are allowed to fall through a kind of a series or a conveyor belt type of approach, where we have some blade here that tries to make sure that the compact or the part that you're fabricating is thin. It is used for very thin fabrications. So slip casting method is used. It is one of the types of slurry casting, and in slip casting you are having a specialized molds, because you want to have a removal of your binder by the action of like by mechanical forces. So you just have to answer what is the correct option, that what kind of a mold is being used and what is the action by which this binder is being removed.
For slip casting, porous and capillary action we use.
uh,
Mold and
Right, that because we are using a porous mold. If you know the mold that we have, it is porous. So all the water binding material, because there is also water being used in these types of like binders. As a binder, apart from the organic material, water is also used. So that water needs to be removed from the mold or a compact. So we have some porous molds used, which will allow the percolation of your water, and then it is also carried out with the help of a capillary action. So you have some capillary action by which the water preferentially moves through those capillaries and thus results in the drying of the mold, say for example. So porous and capillary is the right option. Then we have another question that says if the compaction pressure is increased from 20 to 35 MPa, how is green strength impacted? Consider no changes in arrangement. So we have two things here. We know that the compaction and the green strength are related directly because as you increase the compaction pressure, you will have a higher green strength. So you just have to a simple problem where we have to relate the compaction pressure with the green strength. You know there is a formula relating to your green strength and pressure, that is something like this: minus b sigma naught, which is the rod strength of the material, and pressure. So this b is related to change in arrangement, so we do not have any change in arrangement here. So we just have this factor which is your green strength and pressure, so you just have to relate these two. So you can say the green strength for case 1 and green strength for case 2 is equal to the pressure in first case and the pressure in your second case. That will help you to give the relationship between the strengths. So we know the pressure of case 1 is 20 and for case 2 it is 35. So this is your relationship, 20 by 35. So you just can directly say what is the relationship, how is sigma 1 related to sigma 2. What is the factor that is relating 20 by 35? So this will be 0.57. Is it clear that how the compaction pressure and your green strength are related? So if you increase your pressure from 20 to 30 MPa, your strength will be increased by 0.57. Is it clear?
Okay. So, can you just reiterate, ma'am, this one, the equation?
This is a normal equation that says we have some like a combination of equations that are related to your porosity, to your pressure, because as you increase the pressure, the porosity will decrease, right? So the fractional density of your the fractional porosity will decrease, right? And then we also have a relationship between your strength and your pressure. So the relationship between your strength and pressure is given by this kind of a formula. It says that the strength is related to some b, which is a constant, which is related to your changes in the rearrangement, because you know in the stage 1 of your compaction there is a rearrangement of your molecules or particles happening. So that is related that it is a constant. But we have sigma naught, that is also a strength of a material under like or rod conditions. So we are also not taking into that consideration. We are just concerned what will happen with your strength if you are just increasing the pressure. It is obvious that if you increase the pressure from say 20 MPa to 35 MPa for a compact, your green strength will increase. But we just wanted to know how much will it increase. So it will be just 20 is your initial for example pressure in case 1, this is your pressure in case 2. So the compaction pressure you can calculate the green strength based on their ratio, that is sigma 1 by sigma 2 is partial pressure 1 by partial pressure of 2. So that will give you a relationship between your green strengths. Is it clear?
Yes, ma'am.
For the next question, you can take 2 minutes and then answer it. It says that considering all other parameters constant, the order of highest to lowest green density is molybdenum, copper, tungsten. These are just randomly given some elements. These elements, and in the brackets you can find their yield strengths. So we are trying to see a relationship between your green density or green strength, okay, green strength or green density you can say. So in between their green density, green strength, and we are trying to see a relationship with their yield stresses, yield strength, or you can say, okay. So you have to see,
Copper has the highest green density.
okay.
Then nickel.
So I'll write
Then
it first. I'll write it. You are having copper as the first. So you are saying that it will have a
because
highest.
it has lower yield strength, so
Yes.
that's why its green strength will be highest.
Yes. Okay.
Copper, then nickel,
Okay.
then zirconium,
Okay.
then molybdenum, then tungsten.
Okay. So this is your
Because
order.
if yield strength will be more, what I feel yield strength is more, your work hardness will be developed during compaction,
Right.
and so your gain density will be lower. Am I correct, ma'am?
Right. Right. That is right, because if you have a low yield strength, then you will achieve your compaction quickly, for example, and that compaction will be higher as compared to for other grains. So, for example, for a copper at a pressure of 33 MPa, you can achieve a higher density. But even if you go for 300 MPa, the molybdenum will not be dense, will not be compressed because there is no plastic deformation yet. Actually, basically, we know that compaction is especially in materials in powders or in metals, the compaction is actually a function of your plastic deformation. Just simply how much material is deforming. I'm sorry, I'm not able to write clearly, but this is plastic deformation. So the compaction is a function of your plastic deformation, and that plastic deformation is a function of your yield strength. So if you have a smaller yield strength, then that material will be easily deformed, and that deformation will result in higher green strength. So that is why copper is first and tungsten is last, for example, in this problem. So this will help you to determine if you are working with multiple, say for example, powders, and then you have this will help you to determine how much pressure should we apply in order to achieve a green density. For example, for molybdenum, the density will be the compaction pressure will be very high because it is a higher, it will yield at higher values. But for copper, even at lower pressures, you can achieve a compaction, you can achieve a densification. So this will help you to analyze. So this is very important. The particle yield strength. There are different parameters that affect your green density. One of the parameter is your yield strength. One of the parameter is your hardness. One of the parameters is your obviously compaction pressure, but that is not a property of the powder. So one of the properties is your morphology. So the powder characteristics such as yield strength, morphology, or hardness have an influence on your densification. So that is why you have different routes to prepare the powders, right? If you have different routes, you have different morphologies, and different morphologies will dictate what is your eventual green strength. So all of this will be related. So then we have another question that says, considering all parameters constant, the order of highest to lowest green density is. So now, based on our, this is based on your hardness. Earlier it was based on your yield strength. So now it is based on your hardness. These values are given for hardness. Say for example, we are talking about. So these are hardness values. So we are talking about hardness. So can you tell what is the order of highest to lowest green strength?
And copper will be highest green strength.
Copper will be
Highest green strength. Green
okay.
density.
Green density. Okay, why?
Yes. Because it has hardness. That means its hardness is low, so it can be compacted easily.
Okay.
Particle to particle interaction will be easy.
Okay.
And then comes the zirconium oxide, then silicon dioxide, then aluminum.
So I'll write it. So you are saying the first is copper,
Copper, then zirconium oxide,
then zirconium oxide, ZrO2. Okay.
then SiO2,
Okay.
then Al2O3 aluminum.
Yes. So for a alumina which is having a very high hardness, it is very difficult to achieve densification. Why? Because there is lower amount of because there are large amounts of interparticular frictions occurring inside the material, and that will not allow it to densify as easily as, say, for example, copper. So copper, because of it has low hardness, it will try to get compacted at a lower pressure value and will achieve a higher density, while the alumina will not be able to achieve a higher density because it is having a higher hardness and there are large amounts of frictions between the particles that will prevent their compaction. So is it clear?
Yes, ma'am.
Now we have one numerical question. It says that this is just a hypothetical question, just to have a clarity of your this filling of the mold, which is because we know that one of the parameters is also your mass flow rate. This is your mass flow rate in the mold. This is given by this equation, so it is based on this. So the question says that compare the mass flow rate for cylindrical and rectangular molds. So we have two types of molds. We are talking about two molds. One is cylindrical. So this is your cylindrical mold, and one mold is your rectangular mold. So it is something like this. Okay. So it is saying that it is of same volume and length of the rectangle is same as that of height of the cylinder. So we know this is your height of the cylinder. So we can write it as L, and it is equal to the length of the rectangle, so we can say it is here L. So we can say these are the two parameters that are same. So we are just changing the mold type from a cylinder to a rectangular by considering viscosity of the mix as same. So we are trying to say that we are trying to have a mixture of our powder and binder which is same whether you are using a cylindrical mold or a rectangular mold. So this parameter eta is same for both. So it is saying, and we are applying a pressure of 20 MPa, that is also same. So you just have to compare the mass flow rates just based on their dimensions, because that is the only parameter that is now changing. So you know mass flow rate is equal to pressure divided by the viscosity, and k is your this like geometry constant. It is related to your geometry. We know for two geometries that for a cylindrical it is equal to 128 L divided by pi d raised to power 4, and for a rectangle it is L divided by width times t times cube. This is 3 times the time. Okay, oh, sorry, time, not thickness. Okay, so now we are trying to say that we have to compare the two mass flow rates. So first we'll write for a cylinder what is the mass flow rate for a cylinder. So P is same for both, we know eta is same for both. Now k will be 128 L divided by pi d raised to power 4. So this is your mass flow rate for a cylinder. While we can find the mass flow rate for rectangle likewise, we can say it is P, this is Q for a rectangle, okay, R. PR divided, this will be P divided by this, and then we have our K, that is L divided by the width of this cube. This is your width and this is your thickness. Okay, so that is t cube, and this is your diameter of the cylinder. This is t. So we are given the parameters. Now we have to compare them. So for comparison, we have to write QC divided by QR, for example, because we are trying to compare them. So because this pressure is same for both cases, the viscosity is same for both cases. So we have something like this: pi d raised to power 4 divided by 128 divided by L, and we have this, that is W, which is the width, thickness Q divided by L. So we can just rearrange it first. This is pi d raised to power 4 divided by 120 128 L into multiplied by L divided by W T cube. Because the length is same for both cases, so we can write this L and this L is same, because we have said that the length of your rectangle is same as the height of the cylinder, so we can cancel this out. So now we have just equation based on your diameter and uh, width of your rectangle and thickness of your rectangle. But also there is one thing that is given, there is that it is having the same volume. We just want to conserve the volume, whatever volume of cylinder we wanted to create here, we are just creating the same volume of in the form of a mold, in the form of a rectangle. So you just compare their volumes. So volume of your cylinder is equal to volume of your rectangle. So can you draw a relationship between their parameters based on your volume comparison? You can take 2 minutes to solve it. You just need to know the volume of your cylinder. So the volume of your cylinder is, you know, it is pi r square times
Pi
h.
d square by 4 into L.
Yeah, pi d by 4. You can also do that. Pi r square h. And the volume of your rectangle is length into breadth into height, right? Because in this case we are talking about this is h is here L, so we can write as pi r square L, which is equal to your length of the rectangle, into breadth here we write is at W, and the height is written as D. I'm sorry, I'm not able to write clearly. This is length is cancels out. So now you can say, but we are also given that the width of your rectangle is 5 centimeters. So this W is 5. So now you have a relationship that says pi r square divided by 5 is equal to T. Is it clear?
Yes, ma'am.
Okay, okay. I'll try to write it here. I'll try to write it in a new slide. Can you now calculate? First, I'll write this. So now what kind of a relationship I have arrived at? It was pi r square, something like this. Pi r square was this the relationship? Pi r square by 5 is it equal to T? I think that was the equation. So, for example, considering we are taking the radius of our cylinder as 20 centimeter, just a hypothetical example. So we can put that 20 here. Can you tell me what will be the value of T? It will be 20. So we can write it as pi. It's okay. We can write it as pi. So it will be 80 pi. Is it clear?
Yes, ma'am.
Okay, so now what we were asked in the question to do, we had to compare the mass flow rate. So had a equation for comparison, this pi d 4 128 multiplied by this width and times d cube. So we can write it here. So it was something like pi d 4 pi raised to power 4 128, the length we do not have, So we can write 1 divided by width, we have taken 5, and times the thickness cube. So this is your thickness. So that will be 80 pi cube. It was actually the mass flow rate of your cylinder divided by the mass flow rate of your rectangle, right? So can you calculate now, because you are given D is given, your R is 20, so D you can calculate, that is 40. So you just have to put the value of R here. Can you calculate what is Q C by QR? It will be some numerical value now.
Yes, because we have assumed R as 20 centimeter.
Yes,
Otherwise,
yes.
it will be in the form of D only.
Yes, yes. So for now we are just taking it 20 just to see how it will be related.
It is coming around 0.04.
Uh,
Maybe I am wrong, maybe because I have done it directly. But I think because this, like,
See, for your D, you just have to
no,
put.
no, 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 1 minute, 1 minute.
I'll try to calculate it also.
Okay, let me. Four, five, one, eight, five, eight, five, five, square.
It comes around something like this. It is 7.9 into 10 to the power of minus 4. You just have to take the value of D as 40, right? So this is your relationship between your mass flow rate. So it says that which is highest for a,
Three, four, five.
I think like,
It is, ma'am, 7.91 into 10 to the power minus 4.
yes,
Yeah,
yes,
yeah,
yes.
yeah. It's correct, correct, ma'am. It's correct.
So this says that the mass flow in this particular problem, when you have the same volume for two types of a mold, and you have kept the length of your cylinder equal to the length of your rectangle, so then the mass flow rate will be higher in your rectangular mold as compared to your cylindrical mold, right? So the type of your mold will depend largely on your geometry. The mass flow rate will highly depend on your geometry of the mold. So you need to identify, apart from your particle morphologies, particle, say their this specific area, you also have, or their hardness or yield strength. You also have one parameter which is your geometry of the mold, that is affecting your responses, that is affecting your mass flow rate in a mold, right? So this is one of the parameters. So just a example for your understanding to see that there is an effect of your uh, mold geometries on your mass flow rate. So
Mass flow.
okay, so that is all for today. If you have any questions, then I think that is all for today.
Ma'am, these videos are available in site, whatever we
uh,
have done today.
Yes, yes, we have upload. We will be uploading all the video and also your PPT presentations in your in a Google Drive. So I think you will be able to access it from that.
All these questions which we there now we can practice it.
Yes, right, right.
Okay, okay.
Okay. So I think that will be all for
One
today.
last,
Any
one
question?
last question.
Yes, yes.
Just what percent is binder limit?
You're not audible.
Now is it audible, ma'am?
Yes, yes.
Yeah. It was mentioned that 40% by volume percent is the limit for binder.
Yes, yes.
Uh, is it like 1 to 40 anything? 40 was the threshold
40 was the
maximum, like
optimal.
1 to
That
40.
at 40% you can achieve a successful molding. You can, less than that you will not be able to have a efficient binding capacity. 40% is the optimal uh, like volume percentage of your binder addition.
So it's like a universe.
Mm-hmm.
Uh, any combination, every time it
Uh,
should be 40.
yes, it should be any combination, but yes, it will be dependent because then in a practical purposes when you will be using it, there will be some deviations because of the presence of your moisture, because of the presence of your like large say chains of polymer in your molecule. So there will be difference in the, because this is the addition by volume percent, remember this is not the addition by weight or something, this is by addition of your volume. So I think there will be a slight variation, but this is a generally like established optimal parameter for addition.
Yeah, and similarly, there is lubricant. Last time we said it was
uh,
0.05 or something.
no, no, I'm not, you're not audible.
Yeah, yeah. Last time,
Mm-hmm.
even lubricant was spoken about.
Yes, yes, yes.
So for lubricant also, there was one limit, like I think 5% or something.
Yes,
Uh,
yes. Lubricant
yeah,
is
yeah. So
basically just for
for
your,
my
based on your like wall geometries and based on your wall thicknesses, like wall basically your area of mold. So that will be depending on your lubricant. But for binder, it is by volume percentage. So if you think it is by volume percentage, then it has already taken into account the density of your binder, right? So I think there should not be any large variations from this point, because it is by addition of volume, so the density is already accounted for.
okay,
Mm,
okay.
okay, 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 thank you,
Thank you, ma'am.
thank
Thank
you,
you.
thank
Bye.
you.